Okay, physical science time. Today, our discussion is about work. Something that some of you are much better at than some others. No, this is actually not that kind of work. One of the points I want to make initially is that have you heard the word work? I mean, that almost sounds like a joke, like I'm going to be mean to you about it. So tell me, have you ever heard of work in your life? Have you ever worked a day in your life? I haven't. I'm a teacher. It's a joke, Miss Corfield. I'm sorry. It is hard work to try and wrangle the children. Like, if you think it's hard work to wrangle cattle, try wrangling human children. That's a much more difficult thing, at least in my experience. Would you please tell me the objective? Use a computational model of work to go on, explain the usefulness of simple machines. Does it say? Okay, good, because I don't have any room. I shouldn't even ask, because either way I'm just going to write machines. So we're going to use a computational model, which means we're going to involve computers? Math. Hopefully not computers. I'm really off computers. We're going to use a computational model which will involve math to explain the usefulness of machines. So we have work. Work in the physical definition. Someone should probably tell me, you give me an example of work. When is work done?
Labor.
What?
Labor.
Okay, I like that. Let's have a little list of synonyms. Labor. What else? Well, how would you, I don't know, what does it feel like when you work? You have to... Exhausting. What else? Wonderful, someone said. You like working on your lab? You did work on your lab. Why? Difficult. These are kind of sad definitions of work. Someone might come in here and tell you to pull yourself up by your bootstraps if these are what you feel about work. But let's put that one. Bootstrap pulling up by. Bootstrap pulling up by. I think this is so funny when people say that, because the whole point of the phrase for you to pull yourself up by your bootstraps is that it is impossible. You obviously can't do that. Like, none of you have bootstraps, because that's not the kind of boots you wear. But if you try to pull yourself up by your shoelaces, obviously you can. The whole point of that phrase is that if you're in a tight spot, you need someone to help you out, because you can't pull yourself up. But people use it for the exact opposite of that. Like, man, if you're homeless, you just got to pull yourself up by your bootstraps. And the whole point of the phrase is that you can't do it. Anyway, these are all implying some level of, I'm going to use the word expenditure here. I want someone to define the word. This is not really academic vocabulary so much as, like, I don't know, life vocabulary. What is expenditure? What do you think the root of expenditure is? Expend. Okay, so if we expend something, that's just a very slightly fancy way. Like, you know the word expensive, probably. Like, something you guys know about that's expensive. Lululemon. I was going to use the example Lululemon, but I thought, I don't know if these girls are yoga enough for this. I'll give you one. For me, at least, Nike Ranger mids are expensive, because I wish I had them. I covet the Nike Ranger mids. Birkenstocks are expensive for some of us. They're like $100, but some, like I said about teacher. So if something is expensive, it means that we have to spend a lot on it, right? And that's kind of the root of expenditure, is that we're spending. But in the case of work, what are we spending here? Is this about spending money? There we go. That's exactly it.
I win.
Chloe is the winner of this one. These two things are related. They are not only related, they are, in a sense, synonymous. They are inextricably linked in the physical definition. And the reason I point out all these little examples, or hopefully relationships, poetic metaphors to your life, is that we use this word in a sense that is not completely removed from the physical science definition of work, but it's not the same. So when we talk about doing work, like if you work at Arby's or if you work in the field or wherever people work, at least in our culture, we find work to be these things because they expend our energy. And in physical science, energy and work are related because work is the energy transfer. I'm going to rely on you to remember the vocabulary term energy transfer from the last lesson. If you don't, I can think of some YouTube videos you could watch. I have made personally like 6 YouTube videos about energy transfers, and there are also good YouTube videos about energy transfer. Work is the energy transfer done when an object is what? What's the verb there?
Moving?
Yeah, that's good. I'm going to put moved in the like past participle because moving, it doesn't have to be in current motion, but the energy transfer has been completed. And for another thing, I used this done here, and so I think that should match with moved in the past tense. Yeah, yep, exactly right. Changes position. And from changes position, we're going to get the 2 quantities that in physical science produce work. Changing position means it must have moved some what? Distance. And anytime an object changes position, it is because there has been a force. Or rather, I should have said anytime an object changes motion, which is acceleration, a force, an unbalanced force must have been applied. Now you can probably see that in this definition of work, these 2 things must be in the same direction. If I am the example that I always use and that the book uses and that I think is a good example is if I steal this blue thing, if I steal Bluey and I am lifting it up, which direction is it moving? Up. And I'm putting a force on it, up. And so that work is done. But if I am holding it up, right, which direction am I putting a force on it? Up. And I'm moving forward, am I doing work on it? No, because, I mean, you could make a case that I'm also propelling it forward. But in the first case, I'm going to draw me. This is a self-portrait. I don't even have to draw glasses because I got rid of those. Not a loser anymore. In the first case, I am putting a force up, and it is moving up. Right? Those arrows are not necessarily. I drew them in different colors because they're different quantities. In the second example, this is me again. That time I'm a little bit happier. I got my arm up a little higher because I'm not doing work. Because that's what makes us happy in America is to not do work. I have Bluey again. I'm putting the force up still. At least with my arm, I'm putting the force up. And the distance the thing is moving is to the right. You see that? And so in this case, on the object, have I done work? Yeah. I'll just write it out. Work. Wowie mark. In this example, have I done work? Not in the physical science definition. No work done. Because the force and the direction are not, or the force and the distance are not in the same direction. So could someone think of, Chloe's done a great job answering questions, someone who isn't Chloe, think of a sentence that would encapsulate this hypothesis that we could use as a little litmus test, like a yes or no test of whether work is done. Can someone think of a sentence that we could answer yes or no about whether work is done? I bet you can. What if I give you the first word? Work is. You don't have to come up with a specific sentence. I just want to hear what you say. Work is done. Okay. What's the next word? This is going to be very important for our yes or no question. Okay, I was going to say if, but when is fine. Work is done. Let's put only when. What are our variables? F and D are not just when they're applied, because that's not true. Work is done only when F and D are
Equal.
nope. Yes. Who said? Trey said it. Trey said the right one. Are in the same direction. Now, I'm not going to burden you with trigonometry. There's a guy in this building who will burden you with trigonometry someday if you want. And actually, I will do that in physics. But we revisit this in physics with trigonometry. But we can break up any angled vector quantity. What's a vector quantity? Come on, this is your chance. You think that has direction and magnitude? I don't think you said it quite right.
Yeah.
That's so stupid. Because vectors can be at any angle, you can see that there might be, if we had this at a slightly different angle, well, was some force done in the same direction? Yeah, and so then we would use trigonometry to figure out which part of the force was in the same direction. And so that can be done. But for this class, either they will be yes in the same direction or no, not in the same direction. Okay, so that's what you need to worry about. So if it's in the same direction, and by it, I mean the two things, force and distance, if they are in the same direction, how do we calculate work?
Work equals force times distance.
W is work. F, capital F, is distance. Lowercase d is, really we probably should use displacement, so I'll write that one. Because all of these are what kind of quantities? Vector quantities. They all have a direction. That's the point. That's what we just talked about. Displacement is measured in what?
F is distance. Isn't it force?
Oh, yeah, you're right. I'm sorry. Thank you. It's okay. Displacement is measured in what quantity?
Centimeters?
Sure. Yeah, meters is the base unit in the SI. Force is measured in what quantity? Or sorry, what unit? Newtons. Work then will be, if force is newtons and displacement is meters, and our quantity work is force times displacement, what will our work unit be? Yeah, it's newtons times meters, which is equal to a kilogram meter per second squared, remember that's a newton, times a meter, which is equal to, I'm just running over my own head here, kilogram meter squared per second squared, which is equal to a joule. This you should remember from F equals ma. This you should remember from the last lesson, that a kilogram meter squared per second squared, we had two different ways of calculating it for kinetic or potential energy, is equal to a joule. Sometimes we do express it in Newton times meters. Sometimes we express it as joules, usually joules, because work is the energy transfer. Look, it's like a full circle or like a full half circle. It's like a full crescent moon. Work is the energy transfer. Work is an energy transfer. So we should, of course, measure that in joules. Because remember, we measured energy in joules. And if we're talking about an energy transfer, just like 10 centimeters minus 9 centimeters is still 1 centimeter, we're talking about an energy change. And so that's still measured in joules. So work is also measured in joules. There's our computational model. Now, how do we apply this to machines? Well, the nice thing about work is that you don't like to do it. And so you can get machines to do it for you. Today we're talking about simple machines, which are devices that have one function or one aspect of their change in work. But you could really easily extrapolate this to, you don't want to do your Chapter 5 review and adventure, your learning adventure, which is due tomorrow. And so you have the AI do it for you, right? Because you like things to be labor, exhausting, and difficult, right? No, you like things to be easy, nice and restful, and non-laborious. Yeah, you don't want to do anything. That's why you accidentally always have the AI. But in that context, you having that thing work for you instead of you is making it so you're not getting good at the thing you were supposed to work on. And that's just a little side note that you can ever, if you ever want to get me up on a soapbox, that's the one. That's very easy. But sometimes, if we have, again, this is me. Is this going to show up? Yeah. If we have me, and I don't want to lift box, I got a little bit chunkier from over here and also shorter. If I don't want to lift box, which has a certain weight, I can instead, in a very basic example, use an inclined plane. Instead of lifting the box from here to here, I can now push it up this ramp And how have I changed the work? Is the same amount of work being done? Probably not because of friction, but if we negate friction, the same amount of work is done. Work equals. In this one, I apply a relatively large force over a shorter distance. And in this one, I apply a relatively small force over a bigger distance. You see how they might, if we put numbers in, we might say 4 times 1, and this one is 1 times 4, but guess what? They both end up being the same. So we aren't really changing the amount of work done. That would violate the law of conservation of energy. But we can change how much of it is force and how much of it is distance. That's the point of a simple machine. All the simple machines do this. This will be our example for the video, but there are, of course, that applies to all of the simple machines. Can you imagine how another simple machine, like a pulley, could that change anything about this? Well, I just said this will be the example, but let's do that one too. Pulley. Again, I'm lifting a box. As opposed to lifting that box with just my arms, am I changing the force really? You found in your lab that that's not the case, right? You use the same force. You're just changing what in this case? Instead of lifting it up, I am pulling down. So what have I changed? Direction. So we can either change the direction or the force or the distance, but the work itself does not change. Again, in reality, because of friction, the work does change. You actually get less out than you put in, always because of friction. And that's called efficiency, which your book talks about efficiency. You can read that on your own. But you can use a simple machine to change the the direction or the distance or the force of a simple machine. That's what simple machines do. Have we used a computational model of work to explain the benefits of machines? What's the benefit of a machine? You do less work? No, but you can change the amount of force or distance, and that actually is beneficial. And we call that, this whole concept is called mechanical, meaning referring to machines. Advantage. What's an advantage? A bonus, something nice. What the machine provides that's nice, the mechanical advantage, is this concept. There is math about this. Your book tells about how you calculate ideal mechanical advantage. What could be ideal? Meaning no, probably what? Meaning no. Well, what could we negate if it were an ideal world in physics? No friction. No friction. And so ideal mechanical advantage means negating friction. What possibly could the best benefit of each of these machines be? And that's our ideal mechanical advantage. But the basic concept of mechanical advantage is that you can use a machine, mechanical, to get an advantage in how much force or how much distance you put in. Sometimes it's advantageous to have more distance and less force. Sometimes the opposite is true. Sometimes you want more force and less distance. I will leave you with this example, which is that have you ever, if you are anything like a farm or ranch kid, you might have been like trying to unscrew a nut or something on an implement of some kind. And you can use, this happened with me and my neighbor who were fixing my bike. We could not get the cog off of my bike wheel because it was just on too tight. And so we made the lever longer. Made the wrench longer. We put what some people call a cheater bar on it. We made it longer, and then the nut came off really easy because we increased the distance, which made the force go less. Now, in that exact example, it was actually had to do with torque, but it relates in the same way. That wasn't it. Just beat it. Well, that would be more force, wouldn't it? More force or more distance. And so we made it easier. You made it harder. Yay, Chloe.
What is the equation for power?
Oh, yes, you're right. I'm sorry. We do have that. I'm so glad you brought that up because I would have I just told you I was going to leave you. There is also power. We need to, so it'll just be like a little appendix. Power, I'm so glad you brought that up, Chloe, is either energy divided by time or work divided by time. Why could it be either of these? Why do these both effectively? Yeah, because work is the energy transfer done when an object is moved. And so depending on if we're given work or energy, by the way, do you think if we were given force and distance, we could still use this? Yeah, because I went off course a little bit, but because work is force times distance. How fast we do it is how much power has been expended. And so one thing that makes work in the context that you usually use it feel laborful and exhausting and difficult is how fast you do it. The faster you go, the more power you have expended. And in this case, P is power. W or E is work or energy. And is this, yeah, it is visible. I mean, it's in the glare, but it's at least still on screen. Lowercase t is, what's lowercase t always in physics? I shouldn't say always, but usually time. Time in the SI measured in seconds. Work and energy are both measured in joules. So our unit for power is going to be joules per second. Does anyone know what that is called? A watt. A watt. And it has come up several times during your labs that someone would say, I thought watts was about electricity. And it is. It absolutely is. But it's any amount of energy expended per unit of time. That's why when we talk about these light bulbs or any light bulb, we talk about how many watts they consume would probably be the right word, because it's a certain amount of energy in a certain amount of time. It wouldn't be good enough just to say how much energy they consumed. You have to also have in how long, and we usually use per second. So a joule per second is a watt, and that's power. So when you move something fast, you aren't necessarily, or probably not even, you're doing more work. You're consuming more power. And that also is, by the way, that's how you feel tired when you do something, is because your body consumes a certain amount of food energy. Food energy. Remember, that's where your energy comes from, is your food, in a certain amount of time. And the faster you go at it, the more power, and that's how your body is able to do work. Thank you so much. I appreciate that. What else am I missing?
Since we have had no time to work on.
Okay, that's not for this. Yeah, that's not for this. We will talk about that in a second. But you have more questions about the content? Anyone? Okay.